All right, hello everyone. This is Anna. We're going to talk about part 8, and we're going to specifically focus now on saltatory versus continuous conduction. All right, so thinking about conduction velocity, there are a lot of things that can really impact this. So the first one that we have talked about before is axon diameter, okay? So larger means a faster signal can move along the surface of the plasma membrane. With a smaller, you have a slower signal that can move across the plasma membrane. Both of these are related to surface area. Obviously, a larger diameter vessel, or not vessel, axon is going to have more surface area, more voltage gates, everything comes in faster. Whereas a smaller diameter axon has less surface area, fewer voltage gates, everything goes slower, okay? And basically, this is all going back to that concept of resistance. So a large diameter with more surface area has less resistance to the electrical signal, and the electrical signal being the movement of charged ions along that surface, okay? The other thing that really affects conduction velocity is the degree of myelination, okay? You have unmyelinated axons, and then you have myelinated axons, okay? And remember, myelination is going to reduce resistance, increase insulation, and overall increase speed, okay? So myelinated are faster, unmyelinated are slower signals, okay? Faster signals. Okay. Now, with these, one of the things that's interesting is what it does with the type of conduction. So unmyelinated fibers are going to use what is called continuous conduction, whereas myelinated fibers are going to use a form of conduction that we call saltatory conduction. Okay. Now, they're going to begin at an axon hillock. Actually, both of them will begin at an axon hillock, okay? With continuous conduction, the idea is that you basically have a patch by patch movement as it opens and repolarizes voltage gates, okay? In contrast, the key concept with saltatory conduction is that you are going to boost signals at nodes of Ranvier. Nodes of Ranvier are going to be the only place where voltage gates are exposed to the interstitial fluid where you've got those sodium ions hanging out, okay? With these, as I said, with these action potentials, both start at the trigger zone at the axon hillock, where you first have your very first voltage gate, okay? And they will continue to self-propagate that action potential as long as there are nearby voltage gates, okay? So remember, it's all or nothing. It's going to go to the very end, okay? Now, one of the things with the continuous conduction is one of the reasons it's slow is because it's constantly dissipating the signal because you're constantly having to open voltage gates. So voltage gates have to be closer together. Oh my gosh, my hand is starting to hurt. Whereas saltatory, the voltage gates are further apart because the signal is insulated, okay? And when gates are further apart, you don't have to stop so much. So it's kind of like a bus. So you've got the bus or the train. You've got the, what are they called? You've got the, oh, the word. Oh my God, I can't. I'm totally messing up my thing because I can't think of the word. You've got the one that is going to go between towns, okay? And it's not going to make any stops, all right? This is the express, all right? It doesn't make a lot of stops, so it can go faster. It can get you from one side of Albuquerque to the next. But one that stops at every cross street, every time you stop, you slow down, you lose time, and so it's going to take a lot longer to get from one side of Albuquerque to the next. So this is like saltatory, and this is like continuous conduction. Okay? All right, let's start looking at some pictures. All right, so here we're looking at continuous conduction, and if you look right here, they're showing a nice little bipolar neuron. It is unmyelinated, so you see there's no myelin sheath along its axon right here. It is going to use continuous conduction. So right here they're showing you a picture of the axon. You've got positive charge here, you've got negative charge here. Why do I have a black line right there? That's annoying. Okay. Actually, let's use this. And so what you're going to have is this section. Let's do this. This section is going to depolarize, all right? So that's where it's beginning, okay? It's actually, let me rephrase that. What do I want to call this? We're going to say that this is where you're at resting membrane potential. It could be depolarized. This one is in the refractory period, and this one is actively doing an action potential. This is, again, the resting membrane potential. It's ready to start an action potential. All right, it could do it. All right, so if we go down and we look at the next section, we see that very close by, that's where that lines up, and that's where that lines up. And then right here, and right here, and right here, and right here. So that essentially, as you are depolarizing this, you are repolarizing this, and that's ready to go again. And then this is getting ready to depolarize that. So now, this part is depolarizing, this one is getting ready to be usable again, and this is repolarized. And then this was getting ready to depolarize those voltage gates. So now you've opened those voltage gates, these are getting ready, and these have gone back to resting. So it's basically this patch by patch by patch by patch where you're depolarizing, refractory, repolarized. Depolarizing, refractory, repolarized, and it just continues to go along as you're doing this, okay? Let's look at the next picture. Actually, before we go on and look at the next picture, let's take some notes on the saltatory conduction, okay? And we've already kind of gone over this on the other whiteboard page that I did. So remember, saltatory conduction is possible because of the myelin sheath. The myelin sheath myelinates the axon, and where it exists, it is going to block voltage gates, all right? But it also blocks passive gates. So you can't boost the signal, but you also don't weaken the signal, okay? This causes everything to be faster because you're not leaking, and you can go further before you need a boost to the signal, okay? So at the nodes of Ranvier, you're going to have a gap between two Schwann cells or between two oligodendrocytes. And this is where you can get a recharge of charged ions through voltage gates. Okay, now let's go ahead and start looking at this slide. All right, so we're looking at the axon again. All right, same little bipolar axon, but this time what we've done is we've put Schwann cells along it, so it is myelinated. And we're going to take this and we're going to blow it up. So you can see this right here, this whole tube is the axon. And then you can see the Schwann cell here, and it's been wrapped super tight so that you have multiple layers of plasma membrane, and then the cytoplasm and the nucleus get squished off to the side and form the neurolema. Okay, so this area, all right here, is called the node of Ranvier. And in here, you're going to have voltage gates. Okay, so what's going to happen is the voltage gates are going to be opened, and you're going to have sodium flooding in. Okay, and then the sodium is going to go this way and that way. All right, and you may be wondering, why is it going this way and that way? Well, there's two things going on. You've got a diffusion along concentration gradient, but you've also got something else going on, and that, remember, positives repel each other. And this is really kind of interesting. So I've got all of these are positive sodium ions. And when they're in this little ball right here, they're like, we don't like you because you're also positive. And so they basically, you've got a cell here, or excuse me, an ion there and an ion here. They're both positive. And so they kick each other away so that you end up having them over here. And that helps to not only, and that basically that helps to get it to spread, and it does spread in both directions, but more importantly, you get it to kick itself down to here. The idea is that this sodium here is continuing to depolarize this plasma membrane all along the Schwann cell in order to get to the node of Ranvier where I have my voltage gates, and then it will open the voltage gates and it will give a boost to the signal. If we look here at these sodium ions, you see that you have lots here, fewer, but it's enough to get the signal here in order to open those voltage gates so that you can get an influx of more sodium, and then it can continue to go down. The way this works is you end up having an action potential like this, and then it begins to go down, but by the time it gets here, you do it again, and you get this pulse. And this pulse, this word saltatory, is like a jump. And that's what this jumping is referring to, is this movement as you go along. Okay? All right, let's look at the next little picture. All right, this is trying to show you basically the same thing. So you can see that I have this lining up, and this lining up, and this lining up, so that I've always got something at rest, something generating an action potential, and something going through its refractory period and resetting. Then this is trying to get the action potential over here where I've got new voltage gates. So once the signal gets there, this section depolarizes, and it does it again, and then I get to here, and then the signal is going to go like this, and then it's going to get to here, and then it'll go like that again, and it just keeps going down the line. All right, I'm going to summarize just kind of briefly A fibers, A deltas, and B fibers and C fibers. And the reason I'm doing this is because some of y'all are already in pathophysiology, and we talk about this in patho when we specifically talk about pain, okay? So you got these A fibers, and what you want to focus on is that these are very, very fast, and that means they are definitely myelinated. They have a big diameter. And then you've got your C fibers. These are really slow. They're not myelinated, so they're using continuous conduction. So these are going to be, both of these are autonomic, motor, sensory, pain, light touch. you're going to be using myelinated fibers with big diameters when you need big speeds, like to get your muscles to move, okay? Because you need them to be smooth, you need to be able to get up rapidly, etc. Most of our autonomic nervous system, which is involuntary, that doesn't need to be nearly as fast. And so you're going to move from first heavy myelinated, thick diameter to lightly myelinated, smaller diameter cells. Okay, they still go fairly rapidly, but not nearly as rapid. And you will use this for things that you don't want it to take too long to happen. You want to get information from one area of the body to the next, but it doesn't need to go at Mach 1, just fast. And so you could kind of think of like acute sharp pain here, okay? Now C fibers, information you need to get to your brain, but you don't need to get it there fast. You're not going to waste time on myelination. It's going to have a small diameter. So in terms of, you could think of this as chronic dull pain signals, okay? Or light touch, like you've got a bug crawling on you. Okay, now why do this? Why not have everything be A fibers where they're very thick, big diameter? I mean, why don't you want the information to go fast? Well, it's not about wanting the information to go fast. It's about space in the body. Okay, if you made every single nerve in the body like these, you would have no room in your body for anything else. So in order to have enough space for other organs and other things to go on, you only use these where necessary. All right? And then if you still need to be fast but not as fast, you go down to these. And then any place where you can just minimize size, you use the C fibers. Okay? All right. Let's, I think we've got one more slide where we're going to do a compare and contrast. So let's move on to that. All right, I really, really like this picture because of what it does. So right over here, I've got a bear. We're going to take this little section and we're going to blow it up, okay? So this is like on a dendrite. We don't have voltage gates, so no voltage gates. So these are all going to be local potentials, okay? Or right there I wrote it, graded potential. So I've got a stimulus source here. I get a certain amount of sodium that comes in. And what they've done here is they've made this diameter so that where it's thicker, the signal is stronger. And then you can see it becomes narrower and narrower and narrower and narrower. And then eventually right here, it fizzles out. So whether, so whether this stimulus, oops, let's use a different thing. So whether this stimulus gets to here or this stimulus gets to here, all depends on the strength of the initial stimulus. Okay? So there's your nice little graded potential. Let's now look at some continuous conduction. So right here, conduction is slow. This is continuous conduction. If you look at this axon, you can see there's no myelin sheath blocking the voltage gauge, which is why it's conduction, continuous conduction. So you can see you've got initial stimulus, initial stimulus, initial stimulus, initial stimulus. The strength of the signal is going to be right here. And what you're seeing is you're going to do propagation. So this is still an action potential, okay? So you're going to propagate the signal, and it is starting to fizzle out, but it's close enough to a voltage gate that it can open again, all right? Close enough to a voltage gauge, close enough to a voltage gate. But you see that the voltage gates need to be close together. Otherwise, you wouldn't have a self-propagating action potential. It would just fizzle out. All right, so gates are close together. Now let's look right here at the saltatory. So now we have a myelin sheath. So we've got a myelinated axon. We're going to use saltatory conduction. So here is the initial stimulus. There is my Schwann cell, okay? And then right here and right here, those are both the nodes of Ranvier. All right, so I've got sodium coming in here, depolarizing this membrane. I get an action potential. But what you see is because, all right, let's go back up to this one. And I'm going to put in right there passive leak gates. So the sodium is leaking out and potassium is leaking in, and the signal is beginning to die out. So you have to have another voltage gate close enough to the original one so that that voltage gate can open before it fizzles. But here, when we look at this, we've got a much longer stretch. There might be voltage gates there, but it doesn't matter because the myelin sheath is blocking anything going through those passive gates or any voltage gates. But because there is no leaking, this signal gets all the way over to here where I have new voltage gates before it fizzles out. We pack in a whole bunch of them, and then a lot more sodium goes in, and then that's going to help that signal get from over here to the next node of Ranvier. Now you can see big distance. So this is like your express train, okay? You don't make a lot of stops. This is like a local city bus. It stops every couple of blocks. People get on, people get off. Every time you stop, it adds more time to the trip, okay? All right, that is the end of this particular presentation, and I'm going to go ahead and stop the recording.